should say that this is I should probably say this is joint work with Andres, amongst others. So let me introduce the plan for the next 45 minutes or so. I'm going to talk, first of all, about optics as an abstract interface. I imagine many of you have heard of lenses and other similar concepts. How many people have used the lens library specifically, can I ask? Okay, quite a lot of you. How many of you have been confused by an error message from the lens library? Possibly slightly more of you. So having looked at this abstract interface, for the benefit of those who might not be so familiar with what optics are, I'm going to talk about how the lens library functions as an implementation of this interface, and some of the advantages of its choices and some of the disadvantages, and how we might think about designing a library differently. And so to that end, I'm going to introduce the optics library, which is very much work in progress at the moment, or work not in progress for some time, but hopefully that's going to start changing. Looking at how the thinking about abstraction and distinguishing between interface and implementation can help in our design of our Haskell libraries. And please do feel free to interrupt me with questions as we go along. So first of all, what is a lens abstractly? I imagine lots of you are familiar with this idea, but in case some of you aren't, the basic concept is we've got some way of looking at a substructure of a bigger structure. So in the spirit of type theory, I'm going to present rules for how you form the types of the optic concepts I'm talking about, how you construct them with introduction rules, and how you eliminate them. So given some bigger type S and smaller type A, lens SA is a type. That's the formation rule. The introduction rule says that if I have a function for getting out the A substructure of the S, and a function for putting back an updated value, then I can produce a lens. So that's this lowercase lens function. If I've got some way of building lenses, I need some way of using them, and these are the elimination rules which say view says that if I've got a lens, I can extract out the function for getting the value, and set says that if I've got a lens, I can extract out the function for putting a new value in its place. So far, this basically just looks like a particularly special case of a pair type, but there are, in the background, and not terribly relevant for this talk, some laws for relating the behavior of these get and set functions so that they behave in the way we'd expect of a superstructure and a substructure. That, for example, if you put a value, you should then be able to get it back again. But as I say, a sort of intuitive understanding of what those rules are will suffice for the time being. And then in this presentation, we typically have computation rules which say, well, what do the elimination rules do interacting with the introduction rules? And that simply says that if you call view on a lens you've built, then you get the view function f back, and if you call set, you get the set function g back. So hopefully, so far, this is fairly straightforward and familiar to most of you. But let's have an example, just in case. Firstly is a lens where the bigger structure is a pair of an A and an X, and it focuses just on the A, the first component. So we can build that using the lowercase lens function. The getter is the function to get the value is just first projection, and the function to set the updated value simply takes the pair, ignores the first component, and puts in the new value of the second component. And so, as you might expect, if we use view with this lens and the pair AB, we just get the first component A back, and we can set the first component to C, and we get the pair CB back. So hopefully, again, this is all still fairly straightforward. So why are these an interesting concept at all to identify? First of all, the fact that they're first-class values gives you quite a lot of power, that you can write functions which consume lenses, you can store them in data structures, you can compute them using type classes, means that anything you can do with a normal Haskell value, you can do to construct lenses and work with them. And that gives a lot of flexibility for defining operations on data structures where maybe you want to be parameterized by which particular bit of the data structure you're working on. One particularly useful special case, particularly useful operation is lens composition. That given a lens from R focusing on S and a lens from S focusing on A, then we can build a lens from R focusing on A. The definition is not important at the moment, but as an example, composing firstly with itself gives a lens that focuses in on the first component of a pair inside the first component of another pair. And this gives you a very powerful way of talking about, in particular, field updates in deeply nested record structures. So quite frequently in real applications, you get complex data types with lots of fields and data types inside data types, and writing updates to those fields using the normal Haskell record update syntax just becomes very, very painful. And so lenses are a much friendlier way of doing that. Everyone with me so far, I hope. Any questions? Okay, so let's go on to look at some other optics. It's traditional in talks like this to mention things like traversals and prisms, but I'm actually going to keep things even simpler and just look at some special cases of lens. Here's one of them, the getter, which again, given an outer type S and an inner type A, getter as a type, getter SA as a type. This time we've only got the ability to extract an A out of our S. So these getters are really just functions. There's an introduction rule 2, which, given a function from S to A, constructs a getter, and an elimination form view that gets the function back out again. This is really, really very trivial. It's just saying that here's a type that's isomorphic to functions, but it fits in nicely with this a bigger picture of different kinds of object. I'll not give you an example of a getter because pick a function and that will do. And then similarly, as getters are the special case where we can only extract a value, there are setters, which are the special case where we can put a value or modify values stored in a structure without necessarily having the ability to get them out. So this time the introduction rule isn't quite just the special case of lens, because we've got the ability to modify values that are stored as well as replacing values, which we could do with a lens using the view operation, but here we don't have that. So sets takes a modification function on elements A to A, and to build a setter, you need some way of lifting a modification function on elements to a modification function on structures. And similarly, there's a eliminator called over, which given a setter, gets out that operation. Okay, so we've got these different concepts: lenses, getters, setters. But what about the relationships between them? It should be fairly obvious. So for every lens, we can get a getter or a setter, and just by ignoring some of the information we have about it. And of course, getters and setters don't give us any way of getting back to lenses. So it's almost like lens is a subtype of getter and setter. If we were in a language that had subtyping, we'd like to be able to say that for every lens, we just have access to these other types. And in terms of programming with them, what would be very nice is if, say we have an operation like over which applies to setters, but we have a lens. It ought to be possible to apply over to the firstly lens in order to lift a function that works on A's to a function that works on pairs of A's and X's. But of course, if lens and setter are just different types, then this isn't going to work. And if we're in a language with subtyping, then this just does work. And in practice, these kind of conversions between different optic flavors come up all the time when you're working with these concepts. And so it would be really useful if we have the ability to do this without any syntactic overhead. Again, a sort of particularly interesting case of this is the composition operator. We'd like to be able to compose together optics like lenses and getters and setters in such a way that when we're doing so between two optics that can be composed, we just get the most general concept that we can. So if we compose together a lens like firstly with a getter like to not, just the function that negates its input, then we'd like that to be a getter. On the other hand, sometimes it's not possible to compose together different optics. In particular, if you have a setter and a getter, there's no notion that is a common supertype of both of them that supports the interface of both of them. So it shouldn't be possible to compose together a setter and a getter. We'd like that to be a type error. Everyone with me so far in having described the abstract interface? Okay, so let's go on to think about how the lens library functions as an implementation of this interface. I'm not going to try and explain all the details of how the lens library works, because there are much better talks out there having done that already for starters. And if you're familiar with it, then that's a help, but it's not essential. It's a very clever representation. There's a long history of its development, but the particular thing I'd like to focus on is the observation that all these optic flavors like lens and getter and setter, which I previously defined abstractly, now have very concrete implementations. So they're all type synonyms. Lens is a type synonym with some universal quantification for all f and some class constraint functor f, and then some type involving functions. As I say, it's not necessary to understand the details of how this works, but to observe that there's no abstraction boundary here. There's no distinction between the abstract interface of lenses and the concrete implementation that's been used. And one of the remarkable things about this representation is the fact that in order to define composition for these different kinds of optic, we can just use dot from the prelude, the function composition operator. It's really quite remarkable that this works out at all. And the reason for it doing so is that if you compose together two optics, then the universal quantification and the class constraints simply fit together very nicely with the existing machinery for higher rank types in GHC. We also get the subtyping behavior that I was talking about, because the subsumption rule for higher rank types simply does the right thing. So what are the advantages of this representation? Well, as I say, first of all, it's kind of impressive that it works at all, and that somehow it's possible to do this in such a concise way, and even use dot for the composition of these optics is so allowing lots of code that looks very similar to what you might write in an object-oriented language. This approach has been incredibly powerful as a means of exploring the different kinds of optics that are available. So I'm only illustrating this with examples of lenses and getters and setters, but as I mentioned, there are all these other optics out there and all these other structures which arise if you generalize this same basic representation in different ways, or you choose different constraints. And so the fact that there's no abstraction boundary here is useful for exploring new ideas. As I say, you get this automatic subtyping like behavior, and you get a huge amount of ability to compose together different optics and different things that don't necessarily quite fit into any of these abstract interfaces I've been setting out, just because there are no distinctions between abstract types. So everything is just defined in terms of these type synonyms. And so if you've got something that some operation that happens to work for particular instances of these types, then you can define it and use it in the cases in which it makes sense. And that's incredibly powerful. There's one subsidiary benefit to this, which actually a lot of the time you can define these optics without depending on the lens package at all, because the definitions are either simply concepts that exist in the prelude or in base, or in some cases make use of other libraries, but relatively simple libraries. It's possible to define an optic without incurring that dependency. If you actually want to use them and you want to gain access to the API for making use of them, then at that point you need to introduce the dependency. But it's not completely obvious that this is without downsides as well. And so let's have a think about what downsides this choice of representation has. One of them is that it's a little bit too transparent. I started off talking about an abstract interface, about what it was to be a lens or a getter. But what I'm actually using when I, say, work interactively with these things in GHCI is this representation involving a universally quantified, constrained higher order function. And so if I ask GHCI what the type of firstly is, even though I gave it a type synonym earlier on, a type signature earlier on to define it, GHC is going to say, well, firstly is functor fat arrow, ARFA, and so on. Which is fine if you understand the internal representation, but maybe I don't understand this representation of lenses, I just want to write some code that makes use of the interface. Or maybe I do understand it, but I don't really want to particularly puzzle out how this particular type is built up out of the optics constructions. So if I compose firstly with to not, as we established, if you compose a lens with a getter, we should get a getter back. But the inferred type I get is instead contravariant f, functor f, fat arrow, blah, blah, blah. So it's a shame that we don't get more of the interface, the abstract interface, visible when we start working with these things. And maybe GHC could do a better job of preserving some type synonyms sometimes, and particularly in the example of just using an identifier that I've defined with a type synonym in its signature. But I don't think that's always going to be a good solution. This approach is inevitably going to lead to these kind of inferred types that are hard to read. Another problem is it's too expressive sometimes, that we can write things that actually we would like not to type check. So the example I gave earlier of composing a setter with a getter, sets map composed with to not, that shouldn't type check. But it's never going to be possible to make use of such a thing. But in fact, with the lens libraries approach, it does, and the inferred type you get is for all contravariant and settable f, this construction. And it's not at all immediately obvious that, in fact, there's never going to be any instantiation possible of this, because you can't have an F that's both contravariant and settable. The details of why that is aren't too important, but yes, question. Right, yeah. I mean, so what we're really doing is deferring the type error from the point at which you made the error, when you defined the thing, to the point at which you used it, which might be much later on. Yeah, no, that's true. I mean, ultimately, you're not going to be able to write a type correct program that makes use of this. But it would be nice if the type checker could do a better job of reporting where the errors were being made. I mean, so thinking more about the kind of errors that we're getting, I mean, some of these have become a little notorious, but here's a simple example. If I try applying the set function to a getter, in this case to first, well, what's the error message that I'm going to get? No instance for contravariant identity. Which even for, I mean, if you're experienced with Haskell, it's not entirely obvious that the meaning of this is, in fact, I've tried to apply a function that expects a setter to a getter, and that's simply because the representation choice we've made is that all these things are just represented using this extremely clever representation, but one that necessarily has these constraints floating around that don't obviously have anything directly to do with the abstract interface I defined at the start. On the other hand, we also have the problem that some things don't quite work and we'd like them to. So let's have a look at this term. So I'm going to locally make an alias f for the firstly lens that I defined earlier. And so I've got some pair p, and I'm going to try using f as both a getter and a setter. So what's going to happen in this case? This is actually a simplified version of an error I ran into this week while working on a client project using Lens. It turns out that the problem is that the GHC couldn't match type const char with identity. And then it goes on a bit further with talking about setters and something. So can anyone see what the actual problem is here? Why is this not working, David? Yeah, so the point is that, so firstly was a lens, but that's just a particular kind of polymorphic function. And how are we using that polymorphic function? Well, in the body of the let, we're using it as both a getter and a setter, which necessitates specializing it as a getter and then specializing it as a setter. And at this point, unfortunately, the monomorphism restriction kicks in and says, well, F doesn't have a polymorphic type. And so using it as a getter means that the type it gets specialized to is that of a getter. And then when we try and use it as a setter as well, the error message results. Okay, so I mean this isn't ideal. It's clear that Lens gives us a lot of power, but some of the errors we get from it are not quite so nice. So something we've been thinking about is, well, how could we define a library that actually makes clearer distinctions between these abstractions? So rather than saying, well, lens and getter and setter are all just type synonyms, can we make them proper types in a way that gives them their own unique identities? And that should help with type inference and error messages, because GHC's just got a lot more to work with. It knows that we're treating these things as different types, and we have names for them that it can report. But at the same time, we don't want to give up the nice pseudo subtyping and flexibility of composition that the lens representation gives us. The fact that you can just compose together different kinds of optics, that you can use, say, a lens where a setter is expected, is really, really useful for writing concise code. And the boilerplate involved in just explicitly casting all the time between different types for different optics just becomes too unmanageable. So that's the problem we want to try and resolve, and that's what I'm going to talk about for the remainder of the time. How might we do that? And I should say, so this is a library that we've been working on. It's available on GitHub. I'll give you the link at the end, but it's very much work in progress, and we're still exploring the advantages and disadvantages of different design choices here. But let's talk about how we're doing it at the moment. Well, first of all, let's make explicit in Haskell the hierarchy of these optic flavors that we're working with. So I'm going to do that just by defining empty data types, a lens, a getter, and a setter, just to act as tags to identify the different kinds of optic we're working with. And I'm going to define a class called is for expressing the subtyping relationships between them. So it's a multi-parameter type class with 2 parameters k and l, and I can give it an instance that says it's reflexive, and then for each of the pairs of points in this subtype hierarchy where one type is a subtype of another, I can give another instance. So a lens is a getter, and so forth. And in the spirit of abstraction, I'm not going to, for the moment at least, say how this class is implemented, because from the point of view of the consumer of the library, it shouldn't really matter how exactly it works, just that the types say what's going on. We have tag types for the different optics, and we have a class that expresses when one of those is a subtype of another. We might potentially have quite a lot of instances, given that the number is going to be quadratic in the number of different flavors we're distinguishing. But you tend not to define these new kinds of optic every day. So I think probably we can get away with the number of instances required. So what can we do once we've got this hierarchy of optic flavors? Let's define a new type, which I'm going to call optic, parameterized by the flavor k and the types S and A we had before. And so lens, getter, and setter are still going to be type synonyms, but this time type synonyms of a much simpler form. So they're lens is just optic, a lens. And so that's the underlying concept that we're going to expose to the library user. They're going to see this optic type and the fact that it's tagged in different ways, but not how optic under the hood is implemented. And again, I'm hammering that home by not saying for the moment how the optic new type is implemented, just that it carries some payload which is going to be a representation of either a lens or a getter or a setter or whatever other optic flavor we're working with. And I'm going to use the is class to define a subtyping relation, or to make use of the subtyping relation and define a function sub that's given a k-flavored optic will deliver an l-flavor optic whenever k is an l. How do we make use of that kind of subtyping? Well, we probably don't want to have to write sub every time we need to convert between one flavor optic and another. We could do that, but it just becomes quite tedious. So we want to be able to write over applied to firstly rather than over applied to sub firstly, using the example we had previously. So to do that, one way of making that possible is to generalize the type of over slightly, so that rather than saying it takes a setter, we can say it takes an optic k, subject to the class constraint that k is a setter. And hopefully this sort of expresses in a fairly natural way to a Haskell programmer what's going on with the polymorphism that over provides, and integrates the subtyping in a more familiar way to the Haskell class system. So we're being fairly explicit that this is the constraint that needs to be satisfied for over to be callable. And so I'm hoping that's fairly straightforward. Okay, so moving on from subtyping, then we have composition again. How can we define that? So we need some way of determining for two optics that we're composing together what flavor of optic do we get back. So that's given by this class join. So a 3-parameter multi-parameter type class given a K and an L optic, determine M, the type of the resulting optic. So there's a functional dependency to determine M from K and L, and superclasses to say that M had better be a supertype of both K and L. And we don't need any implementation of the class. That's all the information that's required to define a composition operation. Again, we need a whole bunch of quadratically many instances to actually define the subtype hierarchy. But hopefully that remains fairly straightforward. So what does this mean for type inference? So where Lens was giving us inferred types that mention all these representation details, that means now we're going to see rather more directly that rather than working with a functor f, fat arrow, and so on, we're working with optic a lens. It would be nicer if it said lens, but I hope this is close enough that it's comprehensible. What about this invalid composition we had before? A setter composed with a getter. The error message we get now is going, rather than talking about the constraints involved, well, in fact, in Lens, this type checked and then would lead to an error down the road. Now it's explicit that this composition doesn't type check because there's no instance of the join class. Or indeed, with a little bit of extra detail behind the scenes, we can adjust the error message and say we'll have a class representing the possibility to compose two optics, and GHC's error message says that more directly these things can't be composed. What about applying a setter to a getter, sets applied to first? With Lens, that told us no instance for contravariant identity. Here, we're getting no instance for is a getter a setter, because the is constraint is the thing that's powering the pseudo subtyping. And so again, hopefully that's something that's going to be more accessible for people just getting used to these concepts of lenses. And the monomorphism restriction example just works because no longer is a lens secretly a polymorphic thing that gets specialized by the monomorphism restriction in ways that could be confusing. If we locally make a definition for a lens, then it's a lens because that's what the type says it is. So the advantages of this kind of approach. First of all, somehow the types are expressing rather more directly what they mean in terms of the abstract interface I was talking about at the start. That it's rather than using some extremely clever representation techniques to encode lenses, we're just saying we have a type of lenses. And we don't need to understand the details of how those are implemented in order to be able to work with the public API. And that helps a lot for type errors, for type inference, and just making use of the library. And it gives us a lot of choice under the hood about what implementation we're going to use. So I've been talking about the lens package and its representation a little bit, but there are other ways we can represent lenses. There are more concrete representations, and there are things like prefunctor lenses, which use a similar polymorphic representation to lens, but with a slightly different design. And we're no longer committing so much to those. That's essentially an implementation detail of the library, and potentially, conceivably, even a detail that we could use backpack to abstract over and make different choices possible because the different trade-offs they have. On the other hand, I mean, everything is not always wonderful. We have to do more work to explicitly say what kinds of polymorphism we're going to permit using this approach. We've had to define these is and join classes to express the subtyping and polymorphism of composition. And whereas the lens libraries approach makes possible more or less any kind of operation on lenses that make sense, here we've got to put a little bit more thought into what we're going to permit in terms of ways of combining optics. And so, for example, if you're familiar with index lenses, then that's one area where the public API I've shown doesn't account for them, and we need to change it in some way to do so. There are some interesting design trade-offs there about how we might do that. But it's not something you get access to automatically. It's something you have to think more about at the time of designing the library. And really how I see this is about taking the amazing, vast array of functionality available through the lens library and picking out particular bits of it that prove particularly useful and easy to understand and explain. Some of the other downsides, you have to be fairly upfront about which particular points you want in this subtyping hierarchy, because I'm using just data types to identify them. You can add them subsequently, but you can't insert points into the hierarchy of subtypes. And as I mentioned, you need potentially lots of instances. One final point about the trade-offs. I mentioned at the beginning, earlier on, one of the interesting features of the lens library is that you can define optics without actually depending on the lens library at all. That's not the case here because you need to have access to this optic new type in order to define anything. And so instead we're taking what might be seen as the more traditional approach of defining an optics core package which has a minimal dependency footprint and simply gives you access to the basic functionality. So that if you want to make optics available using this technique, you can do so, and then and we can provide access to conversion operations from optics defined using the lens library. So to summarize, the big takeaway I want you to get from this is that there's always a trade-off with introducing polymorphism into your libraries. And this is perhaps getting into slightly controversial territory, but there's been a notable process recently of people trying to make things as polymorphic as possible, and things like the foldable traversable proposal, introducing more and more polymorphism and making it possible to do more and more things with less and less code, which is great, but it's always a trade-off. That by gaining the expressivity and flexibility the additional polymorphism gives you, you also lose in terms of type inference and in terms of just understanding what's going on. In terms of simplicity. And so thinking about the abstract interfaces that you're building and whether sometimes it's worth making more distinctions and losing a bit of polymorphism in order to have a more comprehensible API is something I think we need to be thinking about. Because I mean, ultimately, one of the real powers of Haskell is the amazing type inference story we have, and the type checker does such a good job of helping us write our code and understand our code. And so in library design, we need to think about whether we're helping the type inference engine do that or whether we're complicating matters. So I'll finish there and point you to the GitHub repo with the code and slides if you're interested in following up on this.
Questions? So in this last slide, I know you sort of your first 2 points you set up as in opposition to each other. No, right on this slide. Don't move. Yeah, polymorphism. You say more polymorphism, less abstraction. But I think they're somewhat orthogonal. So it's certainly true that in the lens library, Edward appeared to have an algorithm which said, if ever I see a type constructor in a type, let me replace it by a letter and abstract have a type class to abstract that. Now that's one thing you can do to any function type. This abstraction business seems to be almost unique to the lens library, and it's what you described as, it's very remarkable that, function composition, ordinary function compose works with these particular representations so that somehow not using abstraction gets you real benefits. I think that's rather unusual. I don't think it's the same as the polymorphism point. So I think this may be almost unique to lens. I really like what you're doing. To say, okay, let's figure out a better way to do that because abstraction is so valuable for the reasons you described.
Okay, that's possibly a fair point. That you can, yes, you can certainly write polymorphic code and still do so thinking about the abstractions that are involved. Yeah. And maybe this isn't such a wider trend.
I think those 2 points are not quite a dichotomy.
Okay.
Another thing I just wanted to mention is that I think in your quadratic number of instances, sometimes you find that you're essentially using a kind of phantom type, or maybe not phantom, but there's the first argument to optic is just an enumeration type, really, isn't it? It's sort of indexes. Yes. So if you just have 20 different variants flat, then you need 20 squared. But maybe there'd be some substructure to them. Some of them would themselves have type parameters that themselves had this subtyping relationship. That might work.
Yes, I mean, there's an interesting point is whether there's additional substructure that you can identify with these tags. And I think, that's valid. Yeah.
Hi, Adam. I wondered if you could comment on why I suppose the easiest thing I would have thought of to do subtyping would have to be over, for example, operations like over to be a class method, and perhaps not have a concrete optics type and get the subtyping that way. Could you comment on why this approach, or that approach didn't meet your goals? Thanks.
So you can do that as well. I think the problem is that then you really have to identify up front what all the operations are that you want to be able at any point to define on your objects. Whereas, so I haven't illustrated it here because I haven't gone into the details of how optic is, the new type is implemented. But actually, under the hood, all that is packaging up is a lens in the same representation that the lens library uses. So you can lift any operation that you can define for on a lens a lens library lens to work in this style. So I think if you were to follow that approach, you would end up making it harder to actually add new operations, and that gives you almost more flexibility and more polymorphism in sort of how you define the operations, and that they can do completely different things for different optic flavors. But it ends up being just too much to define all of those for all your different flavors.
Yeah, so thanks for the talk. It's pretty fun because actually I tried to port lens to Scala, and I can end up with a non-coding, with a representation similar to what you have because of subtyping. Mm-hmm. So yeah, it's actually fun to see that. I feel like some of the stuff that we try to fix here are not really the fault of the library itself, but more about the compiler. So don't you think that maybe some of the issues you fix here could be fixed maybe at another level?
Interesting question. So certainly one of the things that's going on here is that GHC doesn't always use a type synonym to express a type in error messages. I think that's quite difficult to fix in general because it's trivial if you've just got an identifier, but as soon as you've got even a composition, then GHC is going to be type checking that and is going to be inferring a type using the type you've specified, and it's hard to see in general how it could then sort of reconstruct the information of the original type synonym. But there's certainly work that, there's lots of work that can be done to improve GHC's error messages that's orthogonal to this. But I think trying to improve GHD's error messages to the point that it can spot what's going on in one of the error messages I was showing and translate it into something more comprehensible is just asking too much of the type system, really. Yeah, no, I mean, I'm sure there are things that can be done to improve matters, definitely.
Okay, so we'll have to stop here. Please do not run away yet. I have to make an announcement, but let's first thank Adam again.
Thank you very much.